In an earlier video, we have seen MS COCO, the dataset that we'll be using to gauge whether or not a specific object detector is performing well. And in this kind of video, what we are trying to do is to, before we dive into the specific architectures, the neural architectures of object detection that we will deal with a bit later, we need to spend some time on what is actually called the metrics. And the metrics are actually quite important, that kind of discussion, because it kind of transverses all these kind of architectures. And we have potentially tens of architectures in object detection we can deal with. And out of the many, we'll be dealing with a very specific family. So I think it's worthwhile to spend some time trying to understand what are those metrics are. And I wanted to start that kind of discussion by just writing down the key sort of events that we have seen also in the binary classification discussion in that kind of video. I think I can distinguish here in object detection three types of events. The first event is the so-called true positive. So I'm just going to draw here an image. I'm going to use the person class as the class of interest here. And the data set always will contain, I'll indicate this, let's say, a bounding box as far as this object is concerned. This will be, with red, is going to be the ground truth. And my object detector is going to position another bounding box around that kind of class. And so when we have, we will be calling this with the BGT, the bounding box of the ground truth. And we'll be sort of, that bounding box will be accompanied with a class. Let's call it this class person. And if my detector also calls the same, agrees with the ground truth, then I'm going to have a true positive event. I will further qualify, I will use the index I for these true positive events. I'll further qualify what is really happening with respect to how close this predicted bounding box is and the ground truth bounding box is a bit later. But the second type of event I will have in object detection is, as you can imagine, the so-called false positive event, where I have, let's say, a car. The training, my data set specifies that as such, but unfortunately my object detector classifies that as a person. So despite the presence of the bounding box around it, the class ID is different. So this will actually be called a false positive. And I'll use the index J for those false positives. The third is a situation where I have present in the image a person, and as you can imagine, this will be called person in the training data set. However, I have absolutely no detection event, and this will become false negative because evidently I have, I'm predicting negative and I'm wrong. Here I'm predicting positive, but I'm predicting positive for a different class, so I'm actually wrong. That's the false positive. Okay, so that's basically the three events, and there's one category which is actually missing from what we have seen earlier. Well, definitely we do not have the category of true negatives, and the reason why we don't have true negatives is in object detection we are not interested to classify or to detect the not presence of an object. So we're interested only for detecting the objects which are present in the image, and that's why we don't have any true negative. Okay, so I think it's now worthwhile discussing, given the presence of only these three type of events, a couple of thresholds which are going to be becoming important in quantification of these benchmark metrics. So the first threshold is coming, as I mentioned a bit earlier, from the proximity of the detected object bounding box and that of the ground truth. So let's imagine that I have here the class person, and I have a tight bounding box around it, and this is the ground truth bounding box, and my kind of predictor is placing a bounding box like this, and it's correct. The class is correct. I'm going to be defining here, let's call this bpred, okay, I'm going to be defining and the so-called intersection over union. So what is this intersection over union? So this IOU, which stands for intersection over union, it is a ratio of the intersection of the area of the intersection of the bounding box of that I'm predicting and the bounding box, which is the ground truth, divided by the corresponding area of B pred union BGT. So if you want to have a kind of a visualization of that, this was the ground truth, this is my prediction, and this is the what will be the intersection. Then evidently in the denominator I have the ground truth, the prediction, and I'm going to have the union as the in this denominator. Okay, so it's evidently that when the two boxes are right on top of each other, I am going to have the highest IOU, which is going to be 1. And when the two bounding boxes are further away from each other, then I'm going to have the smallest IOU, which is actually 0. And this is, I'm going to be using now the IOU, this concept over here, to define the threshold, the so-called IOU threshold. The IOU threshold is going to be defined as T, denoted as T. And I am going to specify in my metric that when the IOU is greater than T, I am going to classify this as the true positive. And when IOU is less than T, then this will be classified as false positive. So the relationship between the bounding box, despite the fact that I will be getting the class right, is also going to lead to false positives. So it's not only the fact that I got the class wrong, but also the relationship between the two bounding boxes that will also define which events are going to be classified as wrong. So typically we have the threshold belongs to, typical values for threshold is let's say 0.5 and 0.75 for that. So that's of course going to be specified by the benchmark in the corresponding data set. And we will basically need to do the evaluation based on those kind of threshold values and report them. And then we have, if you like, a common ground with respect to how tight my bounding box is within the, how good that predictor is within placing the bounding box very close to that ground truth. But now that we have seen the IOU threshold, and of course, recalling that we have another threshold that is actually associated with how, or the so-called confidence threshold. So I think it's worthwhile drawing a block diagram will actually put this together, and this block diagram will actually govern all the subsequent discussion about metrics. And so here I have a block diagram that it is receiving a y hat, and this y hat evidently contains all the information required for me to sort of count accurately these kind of events necessary for my benchmarking. So the first thing that happens is that it passes through the so-called IOU threshold block, and the parameter for this IOU threshold is the value t. And as we discussed, if we have if the IOU that is defined from the B prediction, the bounding box, the predictive bounding box that's contained inside the y hat is greater than t, then we classify this as a true positive event. Let me call it this true positive event. And this true positive event is going to be give rise to the counter that I will be calling n true positive. And this let me call this incrementing of this counter with this arrow, this NTP, and I will call this NTP a function of t because evidently it is. And in the case where we have the unfortunate situation where the IOU is less than t, we have the false positive event that will give rise to n false positives, which is also a function of t. Okay, so n true positives and false positives are the counter events, which are actually going to be in the second block. That is the so-called confidence threshold comparison block, that it will be calling this threshold comparison tau. So we'll be calling the confidence threshold tau. The comparison is actually happening with this value over here. And the other events which are not affected by any prediction, because we definitely, our detector unfortunately did not predict anything, are the false negatives. Okay, so the false negatives k give rise to the count false negatives, and this is definitely not a function of t, but it will be a function of tau only. And so here I have the false positives are going to be affected both from t and also tau. And here I have the n true positives that are going to be affected by both IOU and confidence thresholds. And now I have this kind of a block diagram that it will actually help me to understand what is really going on with respect to the benchmark like precision and recall values that the dataset benchmark is asking me to calculate. Now that we have the block diagram, let's write down what we understood also from the treatment of classification, binary classification in another video. So let me write the kind of the headline here, what constitutes a good detector. So a good detector can pick up all available ground truths which means that the false negatives should be 0, means that we don't have any events, that we don't have any bounding box over there, while avoiding to detect irrelevant objects. Which means that the false positives should be 0. And in fact, to be more accurate, the counters of n false negatives and n false positives should be 0. So that is basically the ultimate detector if we can actually design it. And I think it's worthwhile kind of trying to see here what is really happening with respect to this kind of thresholds. And if I ask the question as to what will actually be the trend of using this threshold tau to plot this kind of the true positive, the counts of true positives as a function of this confidence threshold, then we can actually all understand that the number of, the relationship should be something like this, some kind of a downwards kind of trend of the confidence. So the stricter we become with respect to what we classify as a true positive or not, then then obviously the number of true positives, the counts will actually become lower and lower. That's kind of easy to and intuitive to understand. What happens now with respect to false positives, with respect to the tau? Now, let's try to think about it, and we'll still see this kind of downwards kind of relationship, like decreasing relationship with the confidence tau. One way to understand that relationship is the claim that the stricter we become in terms of confidence threshold, then all positive detections are going to be affected, both true positive but also false positive. So the stricter the threshold, all positives are being sort of decreasing. And if I may now plot the NFN with respect to tau, then we'll see some kind of a reversal over here. And the reason actually we see this kind of reversal is that when we do increase the threshold tau, since we have less positive detections, we will have conversely a larger number of negative detections. So from that kind of perspective, this is what our intuition actually is telling us with respect to the relationship between those counts and the threshold tau. And this relationship will become important now that we would like to go back into metrics that we have seen earlier, the so-called precision and recall metrics, and kind of write them down in this kind of a new light of being affected both by the IOU threshold as well also the confidence threshold tau. So I can actually write here the precision as the ratio of all the events that have been classified as true positives, so the true positive of I, which is itself affected by T and tau, and summation. I'm not going to write this thing because it's identical, plus from j is equal to 1. Now I am going to define here a new quantity called a new counter called number of detections in general minus NTP. So instead of calling in the false positives, I will be defining here as number of detections as the number of true positives plus the number of false positives. So the number of false positives becomes the number of detections by the number of true positives over here. And here is evidently my false positive event, J, which is itself a function of T comma tau. Okay, so that's the formula for the precision. And if I kind of write next to it the formula for the recall, which itself going to be affected by this, and I'm going to write another ratio. This other ratio is going to be the same numerator as I have seen earlier. and the same over here. This is repeated over here, plus the number of, from k is equal to 1 to n fn, the number of false negative events of the event false negative of k, which is a function. This false negative event is a function of only the tau. Okay. All right, so I will be rewriting this slightly. I'll be writing this slightly to be the same numerator. The same numerator is from I is equal to 1 to ntp of tp of I of t comma tau. But in the denominator over here, I'll define another quantity that is the number of ground truths. Let me write it down explicitly, or number of ground truths for the classes of interest, for the class of interest. And this will actually be the number of true positives plus number of false negatives. Remember that in the false negative event, I do have a bounding box, not from my detector, but I have a bounding box from my training kind of data set. So I have a ground truth bounding box. So I have here ground truth bounding boxes that are associated with the class that I'm trying to detect, both in the case of a true positive event plus a case of a false negative event. So I can rewrite this, since I have true positives and false negatives over here, I can write it here as the n gt, the number of ground truths, and the number of ground truths is going to be a function of t, and I'll explain that now. And this is because despite the fact that the number of false negatives is an sort of increasing function of the tau, the number of true positives is a decreasing function of the tau. Their summation is not going to be affected by tau. It's going to be a constant, and it's only affected from the dependency of the true positives with respect to t. Okay, so that's the reason why we have only a function of t in the denominator here. Something will become kind of important to understand, the shape that this precision versus recall curve is taking. To understand that kind of relationship of now recall versus the confidence threshold tau, then we can expect a relationship that will actually be a decreasing function of tau. And the reason is that the denominator over here is not affected by tau. And the only thing that's affected is the numerator, which is decreasing function of tau. So therefore, if we are to plot the recall curve, then we expect to see something like this. So just the recall versus tau. And it will be a decreasing function of tau. And evidently, the largest possible recall I can actually have is the largest possible true positive rate, which is 1, okay, 1.0. All right, so however, if we are to do the same for the precision unfortunately is affected by tau, both the numerator and the denominator over here. So we cannot really claim that we can a priori kind of provide some form of relationship. But definitely we can actually do the following kind of thinking. So in terms of precision now, we see that definitely the precision is going to be, the largest precision is going to be 1 as well. Okay. And in terms of precision, the graph is going to be fairly, I will call it, exhibiting some form of kind of a zigzag behavior, and what we can, because of that effect of both the numerator and the denominator. So we expect to see some noisy behavior with that it is going to be something like that. And if we are to plot the precision versus recall as a curve, let me just plot it over here, which is precision on the y-axis and recall on the x-axis. So both of them are going to be evidently 1. The maximum will be 1. So the ultimate kind of detector, as we discussed, is someone that it will present to us 0 false negatives, at the same time 0 false positives. So the optimal kind of detector is going to be right here. But evidently this detector is unimplementable and unrealizable because of all the things we've seen even in binary classification, the heavy overlap between classes, and the curve that we expect to see is that we are going to start, because of the zigzag behavior, we are going to get a curve something like that. This curve is plotted by varying the confidence threshold tau. So this tau over here corresponds, this point over here corresponds to tau is equal to 0. And this tau over there corresponds to 100% or 1. And by varying, if you like, the confidence threshold, effectively you are varying the numerator and denominator appropriately of this of all of these two metrics, precision and recall, and we'll be getting a curve like this. And what we define as average precision, and the term average is coming from the fact that we are now having this area under the curve being defined by a lot of different values of the threshold tau. We call this the area under the curve, the average precision, the AP. So the average precision is this kind of area, and we are going to do some massaging of that kind of area to make it a bit more monotonic. So we are, for most of the benchmarks out there, what we are actually going to be defining is we are going to be defining some kind of interpolation method. And if I may draw the end result out of this, is going to be something like this. So it's going to be, so in most benchmarks, what we're interested in to define the average precision is the area under the so-called interpolated, monotonically kind of decreasing curve, which is the red line over here. To shed some more light into what we just discussed, I think it's worth remembering a couple of things. Whatever we discussed up to now is associated with a binary classification problem. And this binary classification problem is between the positive case, where I have the presence of an object of the positive class, let's say a person, and everything else, which is basically all possible shapes of all possible objects, and that's what we call background. So we have a binary classification problem, and to solve for each of the classes that are involved in my data set, let's say 80 classes for the MS-COCO object data set. So I think it's worth remembering what we had discussed about binary classification, and no matter how complicated the sort of representations we're actually building, typically will involve some form of stacking of CNN kind of layers and maybe some form of fully connected layers. At the top, we have of this kind of network, we have this kind of Z, a value to represent the logit that combines all the possible representation across, let's say, combinations of CNN and potentially fully connected layers. And then at the top of the layer, at the top of the network, had this kind of sigmoid, and this sigmoid was actually giving us at the output a y hat. The y hat was the following. If we actually plot what was actually happening, so we were over here we had the z, and over here we had the y hat, or sigma of z. And if I plot the sigmoidal kind of unit, I'll plot something like that with this, basically this is 0.5, and I have this is 0, and I have, let's say, a z over here value that I got in my network, based on all the training kind of process that is actually going on. So this sigma is actually going to define for me a y hat. So this is going to be my y hat, which I'm going to be reporting. And this is basically what is going at the input of this block diagram we just drew on the topic of metrics. All right, so at the same time, we are defining a threshold tau. Let's assume that this threshold tau is right here. So this is basically the tau that I have quoted earlier in this kind of discussion on this kind of precision versus recall curve, for example. And based on that, we will be processing both the true positive and the false positive kind of events. So if my y hat exceeds the threshold tau, then I will, and depending on whether the label agrees with the ground truth, I'll call this a true positive. If I have another detection and that also is the case, the y hat exceeds the tau, but unfortunately the label is not really agreeing with me, then I will be still categorizing this as positive. Of course, I was wrong, and I will be incrementing a different counter. For the cases where I'm still producing output which does not really exceed, however, the tau, then this will be considered a negative event. And this is the reason why we actually saw these false negatives counts as a function of tau kind of increasing. The larger tau I have, the more difficult it is to categorize positive events, either true positive or false positive, and therefore will be categorized as false negative. Now that we've seen the average precision, I think it's worthwhile quoting the so-called mean average precision, or also denoted as MAP, which simply is the so MAP is equal to 1 over capital K, the number of classes, summation from small letter k is equal to 1 to capital K of the average precision K. That the average precision, as we discussed, corresponds to a single binary classification case where the class K is involved versus background. And but I also wanted to quote that in some data sets, more specifically COCO, we tend to also average not only across classes, but also across various IOU thresholds. So we need to be kind of careful to avoid kind of comparisons between kind of data sets, which some of them are quoting mean average precision, and some others they with this kind of averaging, and some other data sets which they involve some kind of different type of averaging. And this is also quite important when you try to pick up an object detector from, let's say, a hub where there are a variety of object detectors are present there, and each one will report kind of a different kind of values. And you should also be careful with respect to using this mean average precision as a metric, because in some instances you're only interested about, let's say, a small subset of the dataset classes. Let's say you're interested to detect pedestrians only versus anything else. And therefore it's worthwhile going beyond the behind the mean average precision and look at the average precision of the classes that you're interested in to select a detector that is able to perform according to your desired metrics.